So we've been talking about groundwater flow and the two different ways to write Darcy's law. Remember, Darcy's law can be written like this, which is negative k dH dx, which is basically the Darcy's law for groundwater velocity. Again, that's Darcy's law. And that tells you how fast the water is moving, right? So things like centimeters per second or something. And if you wanted some sort of volumetric flow, right, how many gallons per second or cubic feet per second, you'd write that as big Q, and it would be the velocity times the cross-sectional area, A, which looks like this. So that would be volumetric flow. Right, CFS, or cubic centimeters per second, or cubic feet per second, whatever. All right, so you can see the relationship there. And this is analogous, as we said yesterday, to a stream. Right. So if you want to know how much water is coming past a given point in the stream, you need to know its cross-sectional area, and you need to know how fast it's going. All right, so it turns out that the hydraulic conductivity plays by far the biggest role in determining how fast water goes. There is a relatively limited range in nature of the hydraulic gradient. So dH dx here varies, but it only varies within a pretty limited range. Hydraulic conductivity, on the other hand, varies by a lot, right? And we talked about this when we were talking about hydraulic conductivity a couple of lectures ago. Hydraulic conductivity can be as high as, say, 10 to the first centimeters per second for a coarse, well-sorted gravel, down to something like, I don't know, 10 to the minus 9 centimeters per second for a densely packed clay, something like that. So it's like a billion or 10 billion times difference, right? That's an enormous difference. So that's hydraulic conductivity is the big thing that really controls how fast groundwater can move. So understanding hydraulic conductivity is a very important part of groundwater, the study of groundwater. And there are a couple of different ways to calculate hydraulic conductivity, and we can do it over a series of different scales. Calculating K over different spatial scales. This is what we're going to be talking about. So there's the very small scale, the medium scale, and then the very, very large scale. So we'll start with the small scale. So to calculate hydraulic conductivity in a section of sediment or rock that's about the size of I don't know, like a jar of peanut butter or a can of tennis balls or something, we use what's called a constant head permeameter. Constant head permeameter. So a meter is something that measures something, right? It's an instrument that measures something. So meter is permeameter is something that's measuring the permeability, which is basically another way to say hydraulic conductivity of something. And the way that we're doing it is we're creating an apparatus that keeps a constant hydraulic head, right? And so this is what I'm going to diagram for you here is a pretty simple setup that was designed that allows you to calculate hydraulic conductivity on really small sections of material. So what you do is you go out you walk out in somebody's field, and you shove down into the ground it's a big metal pole, and at the end of it has a open cylindrical sort of canister, and you shove this thing down into the ground, and it takes a sample of the dirt, right? The dirt gets shoved up inside this thing. You pull it out, and you take it back to the lab, and you take it out, and what you have essentially is, when you turn it upside down, or when you take it out, is you have a section of material. This is all the dirt and everything that was fitting inside this little open hole when you shoved it down into the ground. And you put that thing into this constant head permeameter, and you can measure the hydraulic conductivity on this bulk sample. And so this is the way a constant head permeameter is built. So we have a big reservoir of water, and it has a little outflow over here, and it comes down like this, little tube, and this goes up here. Okay, it looks something like that. So what you do is you have water from a faucet or something, a little faucet here, dripping water constantly down into this reservoir. This is all water. And the water is maintained at this height by this little outflow. So if the water gets too high, you get a little water spilling out here, and it just goes into the sink. So you're constantly dripping water in here, and the water is building up in this little reservoir. And if the water level gets too high, it just spills out. So it's always kept at the exact same height. And then the water flows down like this, and through here, and through here, and then back up here like this. And you have right at the bottom here, you have a little thin membrane, which is, you can think of it kind of like a coffee filter. So it allows the water to go through no problem, but it doesn't allow the sediment that's in this sample that you collected to kind of drift back down this hole. And then you have your sample here. This is where that sample goes, right in there. There's with the little dots on there. And then above it you have another one of those little membranes. Those little coffee filter things goes right in there. And then there's another little outflow here. I didn't draw this very cleanly. I'll use a different color. Where water is going to come out the other side. This is water comes out this side. So what happens, right, is that water is kept at a constant height here, and the pressure of the water, remember, water always goes from higher hydraulic head to lower hydraulic head. So this is the hydraulic head here. This is the hydraulic head here on this side, right? H naught. And this is the hydraulic head where it's coming out over here, H1. So it goes from higher hydraulic head to lower hydraulic head. So the water is going to go this way and spill out. Right? Make sense? And so by measuring the rate at which water comes out on this side over here, we're able to actually calculate the hydraulic conductivity. So if we think about Darcy's law with capital Q, it's what is it? It's Ka dH dx. Again, I'm not going to worry about I'm not going to worry about the negatives because that gets taken care of when you do the subtraction. So I'm just going to drop it for easy to say. All right, so we normally think of dH dx as something that looks kind of like this, where you have, you got a land surface here, and you've got, you got a well here with the water goes up to here, and a well where the water goes up to here, and these are some distance x apart, and there's a difference in hydraulic head, h, right? And so it's the change in hydraulic head over the change in distance, dh dx, that you use to calculate the hydraulic gradient. Now, since we're doing this in the vertical dimension here, since the water's not flowing horizontally, but it's flowing vertically, the way this is often written is we replace this as we replace x with L for some reason. So it's Ka dH dL. So I'm going to draw this diagram here in just a minute, but redraw it. But this is L, right? Basically the thickness of the sample here. Okay, so that's the distance over which the hydraulic head is dropping. It's flowing through a tube here, so it's not meeting any resistance. But when it gets to the sample, that's where the hydraulic head drops. So that's where that comes from. Okay, and we know that Q is what is it? It's like gallons or cubic feet per second or cubic centimeters per minute or something. So it's volume. It's a measurement of volume per time, which we can write as V over little t. So then we can rearrange this. Let's see, is this still visible? Is that even visible? I gotta switch. Push this up here. Okay. So then we can say instead of Q, we can put V over T equals Ka dH dL. Right? So Q is V over T, volume over time, so that's here. And dH dx is now dH dL since it's moving in the vertical direction. Okay? So let's keep that in mind for a second. And we're going to go to the next page. And I'm going to redraw this. I'm going to diagram this constant head permeameter again. So we have something that looks like this. Okay, and the water level is here. Okay, so this is H. We're just going to call it H. You could think of it as DH. But the bottom, the important part here is that the bottom of this tank is the same height as where the water comes out. So this is H or DH. You can think of them as the same thing. Since it's constant, we can just leave it like this. For some reason, they just call it H instead of DH. So remember, this is water, and this is water coming out over here, okay? So the equation that we had before, oh, and then this is DL, right? From here to here, that's L. It's really DL. It's the change in the distance, but we're just going to call it L because this is always the same distance as well. So this equation that we started out with, which was Q equals Ka dH dx, then became V over T equals Ka dH dL. And then since the head is always the same and the thickness of the sample is always the same, this just gets written as Vt equals Ka H over L. Right. Now, what are we trying to solve for here? We're trying to understand the hydraulic conductivity of the sample, so we just rearrange it algebraically, and we K equals VL over T AH. Right. So in words, what does that mean? That means that if you measure the volume of water that comes out over here, this is, volume per time coming out over here. If you measure the volume of water that comes out in a given time, and you know the thickness of the sample, and you know the cross-sectional area of the sample, and you know H, this is kept constant, you just plug and chug, and very, very quickly you can calculate K. Now, how do you know the cross-sectional area? Well, if this thing is round, the area of a circle is pi r squared. And so all you need to know is the radius r of your sample, and you can calculate the cross-sectional area. So an example would be, here's an example, a constant head permeameter has a sample of sand 15 centimeters in length and 5 centimeters in radius, with a head of 5 centimeters, a total of 100 milliliters of water is collected in 12 minutes. What is the K of the sample? So if computer just tidied up here, hold on. Okay, so how would you solve that? Well, you'd say that K equals VL over TAH. And what do we have here? The volume of water is 100 mils. A mil is the same as a cubic centimeter, so we can just put 100 cubic centimeters. 1 milliliter is equal to 1 cubic centimeter. So times the length, which is L, that's the height of the sample, that's 15 centimeters, over the time, which would be 12 minutes, times 60 seconds per 1 minute. That'll give us the seconds down there. The cross-sectional area is pi times 5 squared, and the H is 5 centimeters. All right, so let's do that. So that would be 1500 over whatever this is, and I didn't do these calculations the way I should have. So I'm going to do it really quickly while you're here. Let's see. It would be 12 times 60 times 3.14159 times 25 times 5. And so we would say this divided by this is 0.005. 0.005. Let's see if I can get this back now. Work close. So whatever this is, it comes out to equals 0.005, or 5 times 10 to the minus 3 centimeters per second, which is a reasonable value for the hydraulic conductivity of a sand. Right? Is that visible? Maybe that's not visible. Anyway, right there. Okay, so that is how you use a constant head permeameter to calculate the hydraulic conductivity of very, very small samples. When we come back in the next video, we'll talk about how you do it with samples that you might say be on the scale of your backyard.